time we finished talking about average velocity, and can you guys re-put into words what is average velocity? How would you describe that? This is from last time. Average velocity is, yes, Ben. Change in distance over change in time. Change in position. How about change in position over change in time? Does anybody know from maybe a physics class or I don't know, maybe pre-calc class? There's like a one-word term for change in position. Do you know what it is? Say again? Okay, yeah, but that's two words. One word. Displacement. There it is, yeah. So delta x is the same thing as displacement. So it's displacement is simply your change in location, change in position, and then, of course, to get velocity, you divide by the change in time. Okay, so the average velocity is that average rate of position change between two locations. We talked about this at the end, about how the the billiard ball, when dropped, like the instant the ball is dropped, the velocity is 0, right? But then the moment right before the ball strikes the ground, the velocity is a lot more than that. Didn't we find out the average is like negative 32 or something like that? Yes. Yeah. And so this says, average velocity is that average rate of position change, but instantaneous velocity is the instantaneous rate of position change at one point in time. So it's not between 2 points like a secant line slope, but it's at a single point, kind of like a tangent line slope. Right? So, in other words, to find velocity, we need to find the blank of the position function. You can see it right there. It's the derivative. That's right. So, this is kind of our connection with calculus and these kinematics, is we can actually find derivatives of a position function or a velocity function, and it'll mean something, right? So, the derivative of a position function will give you a velocity function. There it is, symbolized v of t is equal to s prime of t. S is often used as a position function. I'm sure there's a good reason for that. I don't know. We'll use x's and y's or h's or whatever for position as well. Okay, so B says find the velocity of the ball at t equals 1.25 seconds. So let's remind me, because I don't have it on screen right here, what is the position function? It's negative 16t squared something, right? Plus 100, okay. So if you are asked to find velocity, and what you've been given is a position function, we don't panic, right? Because it seems like I gave you the wrong thing, right? We don't panic. We also don't use average velocity because notice this says, what is the velocity at a point in time? So we need a velocity function in order to do that. The way that we get that is the principle we just talked about, and that is a derivative. So I would want you to write something like this. Always label your equations. S prime of t equals v of t. I want to see an indication that you are finding a derivative. Bottom line is, at this point, what is the derivative of negative 16t squared plus 100? Negative 32t. Just using the power rule again. And, of course, the derivative of a constant, like 100, is just 0. So negative 32t. So if I make any statements like that, like I just did, I say something like, hey, of course, the derivative of a constant is just 0. And something in you says, oh, wait, what? Why is that? Talk to me, right? Say something. Ask a question. We can talk about that. So then, negative 32t, that is the velocity at any time. We don't really care about the velocity at any time. We want to know the velocity at 1.25 seconds. So we plug in, right? So it's going to be then v of t, or v of, 1.25 is equal to negative 32 times 1.25 and negative 40. Right? Yeah, negative 40. Is that right? Okay, so that's equal to negative 40. What kind of units would go on that number? Feet per second, yes. So if units are asked for, which I guess they weren't here, so we didn't really have to put them, but if units are asked for, you have to put them. And make sure they're correct. I see plenty of folks that, the units are feet and seconds, and then they say, hey, yeah, the velocity is in meters per second. Unless you do some kind of a conversion, that's incorrect. So you want to make sure you put the right units. Okay, any questions about that one right there before we move? Okay. All right, so the other example here, final example in 2.2 is t equals 0. A diver jumps from a platform diving board. It's 32 feet above the water. The position of the diver is given by that kinematic. If you've ever had physics, that should look pretty familiar. And then it goes on to say S is measured in feet, t is measured in seconds. Find when the diver hits the water and find the diver's velocity at impact. It's a little grim sounding, impact. They're just jumping in the water. And here we go. The first question says, find when the diver hits the water. Any suggestions on what we could do to figure that one out? Peyton, why don't you share? What do you think?
You set it equal to 0.
It?
The equation.
The equation. Okay. So S of t, right?
Yeah.
Yes. We have set S of t equal to 0. So 0 is equal to negative 16t squared plus 16t plus 32. Peyton, why on earth did you choose to do that?
Because that's a position function.
Okay.
And assuming, well, it says that the water is 0, so you're trying to find the time at which you have no height above the water, which is the impact.
It doesn't really say that the water is at height 0, but it does say the guy starts at 32 feet above the water, right?
You could figure it out based on the equation.
I think so, because the initial height is 32, so the water better be at 0. Yeah, that makes sense. All right, so then what would be the best way to solve that? There's lots of ways to do it. I think some are very efficient, others are less efficient. What would you do first? I think I would take it all the way through and divide by it, right? That'll just get rid of it. We can do that because it's an equation. I wouldn't divide by 16, though. I'd go with negative 16. So if you can do this in your head, that's great. If you want to show a step, that's great too. Dividing by negative 16, you get 0 equals t squared minus t minus 2. And this turns into a really far more simple looking quadratic, right? We can factor this pretty quickly. So, Lainey, how does that factor?
T plus 1 t minus 1. I don't think it's right.
You don't think that's right? Why not?
I don't know.
So check this out. Sorry, I put you on the spot. I hope that didn't make you too uncomfortable. 1 times negative 1 is negative 1. It needs to multiply to be negative 2. So rethink. Take a second. Just think about it.
T minus 2 plus 1. And then t plus 1.
You feel better about that? Should she feel better about that? Yes, she should. Lainey, nice work. All right, so then we end up with t equals 2 or t equals negative 1. One of those numbers makes sense. The other one doesn't, given the situation. I think that there's no way that the diver could jump off the board and hit the water a second before they jumped off the board, right? So I think t equals negative 1 doesn't make a whole lot of sense given the situation. So we go with t equals 2. Person is not a time traveler. So then that's great. That's when this person hits the water. But then it goes on to ask us the velocity when they hit the water. So that's obviously a little bit of a different question. We might use this. Jackson, what do you think we could do to get to a place where we could actually find the velocity? Oh, did I catch you sleeping? Sorry.
No, sorry. I was just catching up because I was typing really slow.
Sorry. Any thoughts? Or I can leave you alone. I will call on you guys from time to time, so be ready to go. It's not an attempt to be mean. It's just an attempt to have a conversation. That's all.
Find like the instantaneous rate of change at time equals 2. Right?
Yeah, I agree. So instantaneous rate of change is another way of saying. So, you bring up a really good point because you're kind of like you're working to kind of like how do I want to say this, right? So there is a specific order to what we're doing, right? So he's identified that we need to find a derivative, right? And then he's saying, hey, we got to do something with the 2. So let me ask you this. This is a really important question. This will get more and more important as we go throughout this year. If I'm going to find the velocity at 2, think about the ordering here. Am I going to plug in a 2 first and then differentiate? Or am I going to differentiate and then plug in a 2?
Differentiate and then plug in the 2.
Yeah, differentiate first, then plug in a 2. That's going to make all the difference. So that's the ordering. So Jackson suggested we find the instantaneous rate of change. And so that's what we're going to do. S prime of t then equals, let's just call it out. S prime equals what?
Negative 6.
Plus? And then, of course, the derivative of 32 is just 0 because 32 is a constant. This is where we plug in the 2. That's right. So you plug in the 2, you get negative 64 plus 16, so negative 48. Yes, sir. So negative 48 feet per second. Yeah, the physics thing, if you're messing you up a little bit. Okay. You guys have any questions about that? So a little kinematics, physicsy kind of stuff. Okay, good deal. Well, let's move on then. Let's jump over to 2.3. This is where we had some video material we just talked about. Please notice at number 2, the instructions say find f prime of 1. So the ordering in which you do this is really important. So to find f prime of 1, here are the steps. Step 1, find f prime. Step 2, then plug in 1. That's the order. It has to be that order, because if you plug in a 1 first and then you differentiate, you'll find out later the answer will always be 0, because the derivative of a constant is always 0. So let me zoom in a little bit so we can see that better. But let's try number 2. Let's take a look at it. You know, you having watched the video, you very well might be able to just handle number 2, no problem. I don't know. Let's see, that's good enough. That'll work. But give it a shot. Give you maybe just a minute or two to try to sort through it, and then we'll work on it together. So in number 2, I didn't distinguish this. Is this a calculator active question or not? If this really were a calculator active question, you'll find in the near future that we would take a pretty different approach to this. But so for the moment, let's pretend like this is a no calculator question. Let's think about what the answer would look like if it is no calculator. So the first thing I'd want you to recognize, and I really sincerely mean this is going to maybe sound over the top a little bit, but you're taking a quiz, you're taking a test, everything's out of context, you don't know what section, which problem came from. You're going through, you maybe see a problem like number 2. I would strongly suggest you say, okay, this is like all in your head, you're thinking this, right? You're like, okay, find f prime of 1, okay, I've got to find a derivative, got it, okay, I'm going to have to figure out what the derivative is, there's f of x. You look this over really carefully. If I were you, maybe you underline this, and maybe you do this. With exclamation points or something like that. You're just telling yourself, I recognize that it's a product, and so as I find a derivative of this, I've got to use the product rule. This is the number one most frustrating thing for students over the years, is knowing what the product rule is, knowing how to do the product rule, but then not doing it because they just don't take the time to recognize that this is when it applies. That make sense? Maybe you do something like that. All right, so then once you have recognized it's a product rule, then you would move on and you would actually attempt to do it. So the product rule is 1 d2, so that would just be 2x cubed plus 4x. That's the 1 just rewritten. d2 would be cosine of x plus 2, which is sine of x. d1 would be a power rule, a couple of them. So it would be 6x squared plus 4. Does that make sense? This is all going to flow so smoothly because guess what? We're in the product rule section of the notes. And you're going to be like, well, duh, it's the product rule. But then later on, when all the ordering is different and you don't know which one came from which, identifying the product rule could be a thing that you want to pay attention to. Does that make sense? Okay. All right, so then the final step would be to plug in a 1. So when you plug in a 1, let's see here, we get 2 plus 4 essentially is 6. So 6 cosine of 1. And then, of course, 6 plus 4 is 10, so it'd be plus 10 sine of 1. And if the calculator is not active, this is really about as far as we can go, right? Because cosine of 1, sine of 1, those are not unit circle angles that anybody's going to expect you to have memorized. And so we would just leave it probably just like that, and that would be okay. If the calculator active, obviously you could approximate that, but we're pretending like we don't have it, so we'll just leave it like that. So that is a very conceivable answer you could get on a quiz or a test. It might seem unsatisfying because you're like, well, I'm used to going to decimals and blah, blah, blah. Do you realize that that's an exact answer? That's the exact answer. If you were to plug that in the calculator and get some decimals, that's not an exact answer, is it? Because you had to cut it off. You're like, I'm going to stop after 3 decimals. Well, you just rounded it. It's not exact anymore. So that's actually technically the better answer, as weird as that might sound. Okay, we good? Any questions or anything like that? Okay. So number 3, I think, is another really common situation for questions like this. And this is where, first situation, I think, where you and I, as we name functions, it's really going to matter. You see how within the same question there is a function called f and another function called h. So if you're in the habit of calling every function f, this will be the first time here that you're going to struggle to, oh my gosh, I better name these things correctly. So take a minute. There's a lot of symbolic stuff in here, right? There's not as much of, actually figuring out numerical answers. A lot of symbology here, so please take a minute if you haven't already looked at number 3 to do that. And again, give you a couple minutes to look it over, discuss, and then we'll check. Hey guys, listen up please. So I think something that's very easy, for a teacher to a trap to fall into, that I think all teachers should be aware of this, is it's really important to realize that as you read a question like that, or really any question, or especially if we get into like a word question, it's kind of wordy like a paragraph, it's really important to understand, you guys need to understand this, there's actually techniques to help you understand where to start and what to do. And they might seem really simplistic, but it's really important because if you look at something and you think to yourself, I'm not sure where to start, that's a major issue, isn't it? It's a major issue because if you're not sure where to start, you can't really progress towards anything. And we want you to be able to at least progress towards something you feel like is a right conclusion. So there's a lot of stuff. I mean, you look at this, notice this first word, if. If f of 2 equals negative 3, and if f prime of 2 equals 4, in either of those statements, is there an imperative of telling you what you're supposed to do? Aren't the first little couple of statements there that I've underlined, aren't those more like informational things? Like if this is true and if this is true, there's no real direction yet. No direction as far as, okay, I want you to do this or I want you to do that. No direction yet. And you keep going and it says, and h of x is equal to that. Still no direction. It's simply saying, I'm giving you some information that maybe you'll use later. You don't really get to the what am I supposed to do thing until the very end. What's the word that tells you, here's what I'm supposed to do? Find. And so this might seem really silly, but if you ever struggle, and we'll get into problems where we might have universal struggle later on. If you ever are struggling, what do I need to do? Look for keywords like find or evaluate or what's this or what's that. Look for those keywords and underline it. Don't just look at them, underline it. Say, all right, find h prime of 2. So that's actually what's telling us, that's what we need to do. So find h prime of 2, underline it, put it in a box. We'll have a specific system later on once we get into like applications and things like that. Put it in a box. Hey, that's what I'm supposed to do. And then once you realize what you're supposed to do, now you can take steps to progress towards that, what I'm supposed to do. So if I'm going to find h prime of 2, what's the ordering of things that I need to accomplish? First is find h prime. Yeah. After I found h prime, then plug in the 2. Okay. So I'm going to find h prime. Now that I've discovered what I'm supposed to do, hopefully we can execute the skills we need to get there. So I look at h of x, and I'm like, all right, h prime of x. And I get over here, and I start to look at this in detail, and I'm like, oh man, what is that? It's a product. So I got to use the product rule. Very important that you realize that. And so I'm going to use the product rule, which is 1d2 plus 2d1. And here the symbols can be a little challenging, so let's think this over. So 1 is just cosine of x. What's d2? F prime. We have no idea what f is, right? We have no idea. So the derivative of it would simply be f prime. So f prime of x. So there's 1d2 plus 2. That's just f of x. And then what's d1? Negative sign. So negative sign of x goes there. We're multiplying within that product rule. And now that we've done that, now we can plug in the 2. So h prime of 2 is equal to cosine of 2. And if you want to write this out, you can. You can write f prime of 2, but don't we know from our earlier informational session what f prime of 2 is? So right up here, we're told that f prime of 2 is 4. So if you just wanted to put times 4, I'm fine with that. If you wanted to show an additional step, obviously that's okay as well. And I'm going to move this minus out front here. This is going to be f of 2, which we were told earlier is negative 3. Oh, so that's going to become plus 3, isn't it? And then sine of 2 would go right there. And if we don't have the calculator, that's about as far as we can go. And I would say for sure this would be a no calculator setting. Okay, question now.
Would that still be the correct answer if you didn't have a calculator?
Say it one more
If
time.
you had a calculator and you wrote that, would that still be?
Yeah, totally. You'll find that you're kind of painted into a corner in a lot of scenarios. So like if this was multiple choice and I wanted you to use the calculator, all the answers would be in decimal form. If it was a free response, I don't know, the wording might indicate one way or the other, but like giving an exact answer is always okay. Okay. Do you have any other questions? All right, fair enough. Let's take a look at our next little piece here. It seemed like you're doing okay with product rule. There's some video work on the quotient rule. There was that little check for understanding. Did you all focus on that? You're like, going to be a quiz, going to be a quiz. This didn't feel like we had time today, so I hope you don't feel shortchanged by lack of quiz. Okay, so let's take a look at number 5. So number 5 says g prime of pi over 6 is what we're supposed to find. I mean, notice that word there, find. That's the key word that tells us what we're supposed to do. And then, so this is kind of written in the opposite order of that other question, right? It gives you the what you're supposed to do first, and then it gives you a little information afterwards. I got to say, I guess I don't totally understand why this is, but most folks recognize the quotient rule pretty easily, right? As opposed to the product rule, people just sort of skip over that somehow. But most everybody's like, oh, quotient rule. Why do you think that is?
It just looks more
Longer.
when it's going in and whenever it's separated.
Fraction stuff, yeah. Yeah, the product seems to flow almost like a sum, even though it's not a sum. Yeah, but maybe you do kind of pause and you're like, oh, it's a fraction. And maybe your first thought is, oh, got to do the quotient rule. So let's practice. This would definitely be a no calculator, I would say. I would want to see you execute this skill. So try this without a calculator. Remember the little saying from the video, when you're doing the quotient rule, is low d high minus high d low over the square of what's below. If you're saying the saying and it doesn't rhyme, then you've messed the order up. And of course, because it's subtraction, the order matters, right? So you've got to make sure you got that order correct. So take, again, just a couple minutes, try number 5, and we'll check it. So I don't know if you need to mark this like we marked the product rule, but we want to recognize that it's a quotient rule. You've got a fraction. We can talk about an alternative to this if you want, but for now I'm going to treat it just like a quotient rule. And so I'm going to start off. Remember, the order is to find g prime of pi over 6. You've got to find g prime, and then afterwards plug in the pi over 6. So g prime would be this. G prime of x equals low d high minus high, what's d low? 1, so I'm not going to write anything there. All over the square of what's below. So that would be my first derivative. And just so you guys know, if this were a quiz question and it were a free response, I would say it's probably worth 3 points, and I just earned 2 of them. I just earned 2 of them right there. And so you want to show evidence that you used the quotient rule. That's pretty good evidence that you used it. Your final step would be to plug in the pi over 6. So g prime of pi over 6 is pi over 6 times cosine of pi over 6. And let's do our unit circle stuff maybe right now. What's cosine of pi over 6? Root 3 over 2. Good. So times root 3 over 2 minus sine of pi over 6 would then have to be 1/2. Very good. All divided by pi over 6 quantity squared. And this, again, similarly to before, might seem like a somewhat unsatisfying answer, but I would say in a free response setting, stop right there. Seriously, stop right there. That's equivalent to whatever you're going to come up with if you get a common denominator and add and do a copy.flop after you square the denominator and maybe cancel some stuff out, hopefully correctly. But all of those steps are unnecessary, to be honest with you, because that's numerically correct. Whatever you came up with later is numerically correct. Unless you got to match up a multiple choice answer, just leave it like that. Why not? Okay. Any questions? Okay. Can I tell you about a sickness that is spread through classes? Not every year, but is spread through classes at times. A sickness. It's a real... We have 10 minutes left, right?
Yeah.
35?
Yeah.
There's just kids wandering around the hall. I just want to make sure I'm not going to keep you late. The sickness is this. I don't know what name you would give this sickness, but it's basically seeing the quotient rule way too often, right? Like you overusing the quotient rule when there's an easier way, right? So these next 2 questions are kind of along those lines. Like, what are situations where you could use the quotient rule, but it's not the best? It would be easier to use something else. That's what these are about. So this is more about advice than anything else. Because with number 6 and 7, you guys are 100% equipped to do those. You could do the quotient rule. 4 minutes later, you're done. but the answer is going to be really complicated and it might be hard to match up to maybe a multiple choice answer, and it took you way longer than it should have. So let me give you these examples here. So number 6, you see, let's be sympathetic here. Do you see why somebody might use the quotient rule there?
Yeah.
It's a fraction. There's a top, there's a low, and there's a high, right? You might be tempted. But do you notice here that the numerator is just a constant? It's 10. And the denominator is pretty simple. It's just 3x cubed. So what might somebody do to avoid using the quotient rule and do this more quickly? What do you think, Ben?
You put the x cubed to the top, and then you
Yeah.
so use the 10 over 3 as a fraction.
Yes. So rewrite it as 10 thirds. And when you move the x to the third to the top, what happens? Exactly. So just flip the x to the third up. Just flip it up to the top. And this goes from a somewhat time-consuming quotient rule to what? A power rule. Just like a regular vanilla power rule where you multiply by the exponent, you subtract 1 to get the new exponent. Do you see that? Okay. So yeah, we'd multiply by -3. So y prime equals -10x to the -4. I think we can all agree that that's way faster than doing low d high minus high d low over the square of what's below with that. Jake.
So do you only need to do the quotient rule if you, like, if there's a variable in the denominator? You get all the variables out in the denominator?
Yeah. And if you can successfully and or like easily move the denominator variables out of it, then that might be this situation.
Okay.
Yeah. I will say Bianca actually had a pretty interesting strategy on the previous question on number 5, with the sine x over x. She asked me, like, why couldn't we take the x in the denominator, flip it up and make it x to the -1, and then just do a product rule? And you could. And my advice to her was that sometimes that is better, but sometimes that is worse. You want to be able to know the difference between them. So don't just say, well, I'll just do the product rule. That might actually cause you more work in the long run. So be flexible and be able to do both if you want. Yeah, so it's a good question. Okay, so then number 7. This is even worse, isn't it? Because you could look at this and be like, oh, well, now there's an x in the top and there's an x in the bottom. I have to use the quotient rule. Wrong. Because it's just x to the 3/2 in the top, x in the bottom. What could I do to make this a whole lot more simple? Yeah, just to actually subtract the exponents or cancel out or whatever you want to call it. So then you would put y equals 4x to the 1/2. And I've taken this from a sort of a pain in the backside quotient rule to what? A power rule, which is actually, of course, much easier. So y prime equals 2x to the -1/2. So again, I hope we can all agree that that's way easier than the potential quotient rule that was waiting for you. So I just encourage you to think it through and say, do I really have to do the quotient rule here? Often the answer is going to be, nope, you don't, so don't do it. Hey, I want to make one little point here before we move on to our final topic of the week. Have you guys noticed, a lot of you are really good at this, I'm always trying to be a good example for you. Have you noticed that in every case I have always labeled my functions? There's no floaty functions where it's just like an expression, maybe with an equal sign or maybe not, but it's not labeled. Don't do that. You want to always label your function. So if you're about to write f of x, don't just write blank equals and assume that everybody knows what blank is. Write f or f of x. If you just write f, that's okay. If it's in terms of x, we'll get it. It's f of x. Or if it's y equals or g equals or h equals or whatever, always give it a name. Always label it with the appropriate name. That way there's no mystery. That way there's no ambiguity. If you say, well, I did this because it's positive. I'm going to be like, well, what was it? Was it f, g, h, y, z? What was it? Sometimes there's a clear answer, sometimes there's not. So you want to be really clear with how you label your functions. Okay, so this last little section here, I think this will probably be it for us. Derivatives of other trig functions. You know there's a lot more than just 2. We've talked about 2 of them. There's some of the other ones. There's actually 6 other ones. They're called hyperbolic sine, hyperbolic cosine, hyperbolic tangent. Lauren's making a face over there. We don't cover those in this class. Often Calculus 1 classes will talk briefly about those. They're not that bad. They really aren't. But it's just something else. We don't cover it, though. We're just going to only focus on these. So if it's okay with you, can I just list these out and maybe prove one of them to you? Okay. So here we go. The derivative, and by the way, you want to have these memorized. You don't want to have to re-derive these every time. I'll show you how to derive these derivatives, at least one of them. But you would just want to have these memorized. There's a pattern to it. Here we go. The derivative of tangent is secant squared. The derivative of tangent x is secant squared x. The derivative of secant of x is secant of x times tangent of x. I feel like you got to put in a little bit of effort just to memorize those, but if you can remember those, then I feel like cotangent and cosecant you can see kind of a parallel between them, and you'll see a pattern, and hopefully that'll help you just remember them instead of having to put in that much effort to memorize. So the derivative of cotangent is this, negative cosecant squared. So if you compare that to the derivative of tangent, now you got the co on the front, and it's negative, the sign changed. So the same pattern actually applies to the derivative of cosecant as compared to the derivative of secant. So thinking about that pattern, what would you guess the derivative of cosecant is? It'd have to be negative. There we go, Zach, you got it. Oops, I just messed up. Cotangent of x. Okay, so all of these are provable using the quotient rule. And if it's okay with you, I'll just prove one of them for now. If you want to see others proved, happy to do it. You could probably do it on your own. I'll just do the first one. So here's what I would do. The derivative of tangent, I'm going to look at tangent and say, I know that I can break tangent down into sines and cosines. What is tangent in terms of sine and cosine? Sine over cosine. So I would say what I'm really doing here is the derivative of sine over cosine. And now I've turned it into a quotient. So I'm going to use the quotient rule. So it's going to be low d high minus high d low all over the square of what's below. This goes pretty quick now. What do you see in the top? Isn't it cosine squared plus sine squared? Pythagorean identity, right? What's cosine squared plus sine squared? 1. So we can replace the entire top. This is like magical. As complicated as that looks, we can replace the whole thing with just a 1. 1 over cosine squared x. And the reciprocal of cosine is secant. And so we end up with secant squared of x. Like I said, all of those are similarly provable. You can do it if you want. You can do it on your own. You can think of it as a little math puzzle if you want to try it yourself. So next time we'll look at higher order derivatives. We'll do some applications. We'll come back to tangent lines again. But for now, have a great weekend. See you on Monday.